Today we are going to continue the study of rigid bodies, and what we want to do today is to study what happens with the inertia tensor if it suffers a change of basis. Let me explain what I'm talking about. Remember that we have a rigid body, and we said that we can fix a coordinate system that we established that it was a primed coordinate system like this, and let's say that we can maybe put a different coordinate system that is going to be also fixed to the rigid body like this. Okay, so this means that when the rigid body moves, well, these two coordinate systems are going to stay on the same position with respect to the rigid body. Okay, perfect. This is what I mean with having two coordinate systems in the rigid body. Okay, so looking at these coordinate systems are going to be represented by orthonormal bases, we can establish a relation between the elements of these two bases. And actually, these relations are going to be determined by an orthogonal matrix. Okay, so first of all, we are going to name tilde this coordinate system that is new. We are going to, if this is the prime normal coordinate system, this is going to be the tilde prime coordinate system. So we can establish a relation between the two coordinate systems like this. We are going to have that EJ tilde is going to be equal to BKJ EK like this. Again, these B's represent the elements of an orthogonal matrix that I'm about to write, but it's also important to mention that these components are independent of time, okay? They don't change on time. Again, because these coordinate systems are always moving with the rigid body. So during the motion of the body, well, they are not going to change on time. And well, these elements of the matrix are going to be represented in this matrix like this. B1, 3, and let me complete the matrix. Okay, this will be the matrix that represents the transformation from the normal basis to the tilde basis. And looking that we can transform the components of the basis, we can also transform the components of a position vector that is located at the origin of these two coordinate systems. Okay, so as I mentioned, there is an equation that relates the components of each coordinate system that is going to be xk prime tilde b j prime k prime x j prime. Perfect. So this will be a very important equation for what we are going to do. Okay, and well, let's remember that we defined that the inertia tensor ij, well, the components of the inertia tensor is defined as the sum from alpha equals to 1 up to n if the rigid body is made of n particles. In this case, this is the expression for a discrete rigid body that, again, it is made of n particles, okay? So this R vector locates one of those particles that we name that this is R alpha, okay? So alpha goes from 1 up to n. Perfect. So this covers all the particles that compose the rigid body. So here we have the mass of the alpha particle times the Kronecker delta I prime j prime r squared minus xi prime xj prime. This is the definition of the components of the inertia tensor for the prime coordinate system. So we wonder what happens if we want to calculate the inertia tensor of the new coordinate system in terms of this inertia tensor that we already know. Well, what we can say is that these new components of the new inertia tensor, tilde, is going to be equal to the sum from alpha equals to 1 up to n of m sub alpha times the Kronecker delta I prime j prime r alpha squared tilde minus, well, xi prime tilde xj prime tilde. So we just need to find these three quantities, this one over here and these two terms over here. Okay, so here comes the most interesting part of the lesson. Here we have a Kronecker delta ij prime. So look what I'm going to do now. We are going to examine the term b I prime m prime that multiplies b j prime m prime. Okay, remember that these elements b represents the elements of a matrix, and that matrix is an orthogonal matrix. So if we want to express this term on a different way, for example b m j prime, we will have to take the transpose of this. Okay, so we can say that this is equal to b I prime m prime and then b m prime j prime transpose. Okay, perfect. Maybe this is an abuse of notation because right now, well, this represents a product of matrices, like for example b times b to the t, which is the transpose of b. But what I want you to notice here is that, well, remember that b is orthogonal, so that means that the transpose of b is equal to the inverse of b. Okay, so this. So if we multiply an element of the transpose of b times b, and then, well, we sum for the index m, what we are going to get, well, is an element of the diagonal matrix if I is equal to j. Okay, so that means that, well, we are going to get a Kronecker delta I prime j prime. You can see this as multiplying b times b to the t, that is going to be equal to the identity matrix, because again, this transpose matrix is the inverse of b. So we get the identity matrix. And remember, the elements of the identity, well, are equal to 1 if the row is equal to the column. So that means that we need to the I to be equal to the j to be equal to 1. So we get a Kronecker delta. Perfect. So that means that we can replace this Kronecker delta that we have here for this product that we have here. So we are going to get that this is equal to the sum from alpha equals to 1 up to n, the mass of alpha, then b I prime m, b j prime m prime, and then r alpha squared. But looking at, well, it's the magnitude of the vector r, well, it is invariant. It is invariant on a change of basis. Remember, r alpha tilde squared is equal to r alpha squared. Okay, this magnitude is not going to change, it's going to be invariant. So that means that we can express this as, for example, xk xk. Okay, so let's just say that this is going to be equal to r alpha squared here. And what happens with these two quantities over here? Well, we are going to use the formula, this formula, to replace the value of these quantities. So we will have here minus, and we are going to get b, let's say m prime, I prime, and then xm prime. Okay, so here we get xj prime, that can be written as b times, let's say, l prime j prime x L prime, like this. So let me rewrite the inertia tensor tilde here. Okay, this is what we get for the inertia tensor. So first of all, what we can do from now is to let's see what happens with this term. This term can be seen as bj prime, let's say L prime, Kronecker delta, L prime, M prime, like this. Okay, so we can substitute this to get that this is going to be equal to the sum from alpha equals to 1 up to n of the mass alpha, bi prime m prime, bj prime l prime, r alpha squared, Kronecker delta l prime m prime, minus b m prime I prime, b l prime j prime, x m prime x l prime, like this. So look that here we have bim prime, bmi prime, and here bj prime l prime, bl prime j. What we can say about this is that this is a very similar to the definition of the inertia tensor for the Lm components. Look that if we take out this quantity and this quantity, we get exactly the definition of I, L prime, M prime. Okay, so if we can take this out as a common factor, well, we will have that common factor times I, L prime, M prime. So we can just rewrite this as bi prime m prime bj prime l prime. It is the same. So if we do that, we have the same factor here and here. So we can take that common factor out. So we are going to get I prime j prime tilde equals, well, it will be bi prime m prime bj, let me avoid saying prime all the time, so this is going to be the sum from alpha equals to 1 up to n, m alpha, Kronecker delta lm, r alpha squared, minus xm xl, like this. So as I mentioned, we can identify this quantity over here as the inertia tensor Lm, but in the normal coordinate system, this coordinate system that is represented by this basis. Okay, so that means that we have found an equation that relates the inertia tensors of each coordinate system like this. ei prime j prime tilde is equal to bi prime m prime bj prime l prime times I L prime M prime, where these components of course correspond to the components of the orthogonal matrix B that we introduced at the beginning of the video. So this will be the final important result of this lesson, formula to change the inertia tensor from one basis to a different one that are related with these elements of the orthogonal matrix that relates the two bases.